We know that when we have hydrogen and oxygen react to produce water, that we can't get away with having just a single hydrogen molecule. We need at least two of them so that each pair can pick up one of the oxygen atoms. If we try to scale this reaction down, we would have to cut our oxygen molecule in half, and we can't do that. We have to leave our substances intact. Well, that gives us an equation which tells us that for every 2 hydrogens, we need 1 oxygen, and that gives us 2 waters in result. And because we know that is a fixed relationship, if we know the quantity of any one of these substances, we can use that ratio to convert it into any other substance. Unfortunately, it's very unlikely that when we take our jar of oxygen and our jar of hydrogen and we combine them together in the laboratory, that we have exactly 2 hydrogen molecules for every oxygen molecule. What's more likely is that we are going to have an excess of one of the substances. Now, if we have an excess of something like hydrogen here, we're obviously not going to produce more water molecules. And if we were to assume that everything in this container reacted in order to produce our products, and we just measured the mass of this container and said that's the mass of all the waters we made, we would be very confused because in our mass measurement, we would be measuring 2 hydrogen molecules along with those 2 water molecules. So what we would like is to have a way of determining exactly how many waters we're going to get. And we know that that's going to be determined by the oxygen. The oxygen is going to react with these 2 hydrogens and produce 2 water molecules. And these excess hydrogens are just going to remain excess hydrogens. That makes oxygen what is called a limiting reactant, the substance which runs out first in reaction. And a limiting reactant determines the amount of product we get. So we want a way that we can figure out which of our reactants is the limiting reactant, and that way we can calculate how much product a reaction is actually producing. Our method to determine the limiting reactant is actually pretty straightforward. First thing we need to do is we need to write the balanced reaction equation. We always do that when we're converting between different quantities of moles of different substances. Once we've done that, we can go ahead and calculate the amount of product which is going to be produced. And we're going to do that for each reactant, assuming that however much we have of it is going to completely react. And so we'll see how much total product that would yield. And if any of those gives us a smaller number, then we know that that is the limiting reactant. Now, occasionally, you will have more than one product. You'll have 2 or 3 or more products. In that case, you can choose any one of those final products to do your calculations with. You're still going to find the correct limiting reactant no matter which one you choose. As an example, there's a rather intense reaction which can be performed using rust, ordinary rust, iron oxide, and aluminum. It's called a thermite reaction. So you would have these substances in powdered form, and you would ignite them, probably using a strip of magnesium. And when you do that, you get a reaction that's so hot, it reaches above 2,000 degrees Celsius or 4,000 degrees Fahrenheit. And this reaction is used for things like welding automobiles, welding railroad ties. If you were in the military, you might use a thermite grenade to sneak behind enemy lines and fuse their artillery together, rendering them useless. And since it doesn't involve an explosion, that could be a much stealthier way to accomplish that. Well, because this reaction is so hot, the iron it produces, it's one of the products, will be molten, and it will also produce aluminum oxide. Now, if we perform this reaction using 20 grams of our iron oxide and 8 grams of our aluminum, what is going to be the limiting reactant? Well, the first thing that we're going to need is we're going to need a balanced chemical equation. It's the only way that we can compare quantities of different substances in a reaction. Now, the aluminum oxide, aluminum is 3 away from the noble gases, going from left to right, and oxygen is 2 away, going from right to left. So oxygen would have a -2 charge, aluminum would have a +3 charge. And so to make them cancel out, we can have 2 aluminums and 3 oxygens. So that's +6 and -6. Gives us a neutral charge. So we have all our compounds right. Now we need to throw in some coefficients. Well, we can see that we have 2 irons on the left and only 1 on the right. So go ahead and double the number of irons on the right. And we also have 2 aluminums on the right, but only 1 on the left. So we'll go ahead and double the number of aluminums. And we have 3 oxygens on both sides. So this is a good balanced reaction. Now that we've worked out our reaction equation, we can go ahead and figure out how much possible product we could get, starting with either our 20 grams of iron oxide and using all of it, or starting with our 8 grams of aluminum and using all of it. So we need to choose among the 2 possible products that we had. We could produce either iron or aluminum oxide. Let's go ahead and choose iron. We could just as well choose the aluminum oxide. And we'll see how much we get from our starting reactants. Well, for our aluminum, so take our 8 grams of aluminum and divide by the molecular weight from the periodic table to get into moles of aluminum. Now let's look back at our reaction equation. Our reaction equation said that for every 2 moles of aluminum, that we would get back 2 moles of iron. So we'll include that ratio to convert from moles of aluminum into moles of iron. And then finally we need to get from moles of iron into grams of iron. So we multiply by the molecular weight of iron from the periodic table. Now we come up with 16.6 grams of iron. So that's the amount we'll get if this 8.0 grams completely reacts and it runs out, and then that's where the reaction shuts off. Now our other option is the Fe2O3 is the limiting reactant. So let's say we have our 20 grams of Fe2O3. We'll do the same thing, divide by its molecular weight to get into moles. And then looking at our reaction, for every 1 Fe2O3, we get back 2 Fes. So we include that ratio. And now that we have moles of Fe, we'll go ahead and multiply by the molecular weight. And we get 14.0 grams. Now because 14.0 grams is less than 16.6 grams, that means that this is the substance that runs out first. Our iron oxide runs out first, and it's the limiting reactant. When you have a lot of reactants, where you have to test a lot of different quantities, the previous process can be a little bit laborious to do frequently. So there's a shortcut, which doesn't save us every step, but it saves us at least a few at the end. The shortcut is that you write your balanced reaction equation, just like before. You're always going to need a balanced equation. But now the only thing that you calculate is the number of moles of the reactants. And if you put that over the coefficient for every result and compare those numbers, then whichever gives you the smallest quantity tells you that that substance is the limiting reactant. Say we have another reaction, this time with 3 grams of aluminum reacting with 5 grams of copper 2 chloride. This produces aluminum chloride and copper as products. Which is the limiting reactant between the aluminum and the copper 2 chloride? Let's go ahead and use our shortcut method to do this. But as always, we need to start by writing a balanced equation. So our balanced reaction, we have 2 aluminums react with 3 copper chlorides to give us 2 aluminum chlorides plus 3 coppers. Now that we have our balanced equation, we can use that to calculate the quantities of the moles of our reactants over the coefficients. So we can go ahead and start with aluminum. Now if we look at our equation, we see aluminum has a coefficient of 2, so that will go in the denominator. Now we calculate the number of moles of aluminum. We have 3 grams of aluminum divided by the molecular weight, the periodic table, over 2 gives us 0.056. Now do the same thing for the copper chloride. we had a stoichiometric coefficient of 3 in our equation, so we'll divide by 3. And we'll get the number of moles, 5 grams of copper chloride, divided by the sum of the weights of the copper and the 2 chlorines, which comes out to 134.45 grams per mole. So we get a value of 0.012. And now we just compare those two values. And since the 0.012 is less than the 0.056, that means that our copper chloride is the limiting reactant. Just some terminology now. The theoretical yield is the amount of the product that we get once we know the limiting reactant. So that we've already been calculating. Now when we actually perform the experiment in the laboratory, then the amount that we get and we measure at the end of our experiment is called the experimental yield. Now it's often useful to report how close our experimental yield was to our theoretical yield. So to do that, we calculate the percent yield. And this is just a ratio. You take the experimental yield, divide it by the theoretical yield, and multiply it by 100. And sometimes you lose bits of substance because they've evaporated or they've adhered to your glassware or your instruments are inaccurate. And sometimes you are accidentally measuring substances that you didn't intend to measure that were also produced or incorporated into your product. For example, you might have absorbed some extra water weight, and those can all be factors that lead to you having a different experimental yield than your theoretical yield.